Welcome back. In this video, I'll talk about the Spark Adaptive Query Execution. Spark Adaptive Query Execution, or AQE, is a new feature released in Apache Spark 3.0. It offers you three capabilities: dynamically coalescing shuffle partitions, dynamically switching join strategies, and dynamically optimizing skew joins. But what are these features and why do we need them? What problem do they solve? So let's try to understand the problems and then I'll talk about how AQE solves those problems. Let's assume you are running a super simple group by query in your Spark code. Here it is. Or you might have written a data frame expression similar to the following. So what are we doing? I have a call records table. This table stores information about the cell phone calls made by different users. We record a lot of information in this table, but here is a simplified table structure. So we record call ID, then the duration of the call in minutes, and we also record which cell tower served the call. And my Spark SQL is trying to get the sum of all call durations by the tower location. For these 4 sample records, you should get the result as shown here. Make sense? Great. But do you know how Spark will execute this query? We already learned that. Spark will take the code, create an execution plan for the query, and execute it on the cluster. The Spark job that triggers this query should have a 2-stage plan. It looks similar to this. The actual plan for the large volume of data might not look the same. However, you will have 2 stages. Stage 0 reads the data from the source table and fills it to the output exchange. The second stage will read the data from the output exchange and brings it to the input exchange. And this process is known as shuffle sort. Why do we have this shuffle sort in our execution plan? Because we are doing a group by operation, and group by is a wide dependency transformation. So you are likely to have a shuffle sort in your execution plan. The stage 1 is dependent on stage 0. So stage 1 cannot start unless stage 0 is complete. Now let's dig deeper into these exchanges. Let's look at the input exchange. The input exchange might look like this. I'm assuming that my input data source has got only 2 partitions. So the stage 0 exchange should have 2 partitions. I'm assuming that I have data for 5 towers. So each partition in this exchange might have some data for tower A, tower B, tower C, and so on. Make sense? This is how my exchange looks. Nothing fancy is happening here. My stage 0 will read data from the source table and make it available to the exchange for the second stage to read. I have only 2 partitions in my input source. So the exchange shows only 2 partitions. Make sense? Now the shuffle sort operation will read these partitions, sort them by the tower location, and bring them to the input exchange of stage 1. The final result should look like this. Wait a minute. What is this? Let me explain. Let's assume I configured Spark SQL shuffle partitions equal to 10. I know the default value for this configuration is 200, but I also know I do not have 200 unique towers. I'm running a query to group by towers. So I reduced the number of shuffle partitions to 10. So the shuffle sort will create 10 partitions in the exchange. Even if I have only 5 unique values, the shuffle sort will create 10 partitions. 5 of them will have data and the remaining 5 will be blank partitions. Make sense? Now let me ask a question. How many tasks do you need to execute this stage? Any guesses? We need 10 tasks. Why? Because we have 10 partitions in the exchange. Make sense? And that's a problem. 5 partitions are empty, but Spark will still trigger 10 tasks. The empty partition task will do nothing and finish in milliseconds. But Spark scheduler needs to spend time scheduling and monitoring these useless tasks. The overhead is small, but we do have some unnecessary overhead here. I improved the situation by reducing the shuffle partitions to 10 from the default value of 200. But that's not an easy thing to do. Why? Because I cannot keep changing the shuffle partitions for every query. Even if I want to do that, I do not know how many unique values my SQL will fetch. The number of unique keys is dynamic and depends on the dataset. How am I supposed to know how many shuffle partitions do I need? that's almost impossible for the developers to know in advance, right? We have another problem here. Look at these partitions. Some partitions are big and others are small. They are not proportionate. So, a task working on partition 1 will take a long time, while the task doing the partition 2 will finish very quickly. And that's not good. Why? Because the stage is not complete until all the tasks of the stage are complete. 3 tasks processing partition 2, 3 and 4 will finish quickly. But we still need to wait for partition 1 and partition 4. And that's a wastage of CPU resources. The situation becomes worse when one partition becomes excessively long. For example, look at this. And this diagram represents a data skew problem. In this case, one of your towers is processing many calls, while others have smaller datasets. I'll come back to the data skew in the following video. But for now, let's focus on the shuffle partitions. So here is my shuffle partitions problem. My query resulted in 5 disproportionate shuffle partitions. I made an intelligent guess and decided to reduce my shuffle partitions to 10. However, the situation is still not very good. Make sense? Now the question is this. How do I decide the number of shuffle partitions for my Spark job? Spark 3.0 offers adaptive query execution to solve this problem. You must enable it, and the AQE will take care of setting the number of your shuffle partitions. But how that magic happens? Super simple. Your input data is already loaded in stage 0 exchange. Stage 0 is already done and data has come to the exchange. Now, Spark will start the shuffle sort. So it can compute the statistics on this data and find out some details such as the following. And this is called dynamically computing the statistics on your data during the shuffle sort. Such dynamic statistics are accurate and most up to date, right? When Spark knows enough information about your data, it will dynamically adjust the number of shuffle partitions for the next stage. For example, in my case, Spark might dynamically set the shuffle partitions to 4. And the result of that setting looks like this. So what do we have? We have 4 shuffle partitions for stage 1. Those 5 empty partitions are gone. Spark also merged 2 small partitions to create 1 large partition. So instead of having 5 disproportionate partitions, we have 4 partitions. And these 4 are a little more proportionate, right? So let me ask you the same question. How many tasks do you need to run this stage? Any guess? We need 4 tasks. Task 3 working on partition 3 will finish quickly, but the other 3 tasks will take almost equal time. So we saved 1 CPU slot and we also eliminated the useless empty tasks. Make sense? Great. I talked about 3 benefits of implementing adaptive query execution. Here they are. And I hope you now understand the first benefit of enabling adaptive query execution. Let me quickly summarize it for you. Spark Shuffle Sort has a critical impact on Spark query performance. One fundamental tuning property of shuffle operation is the number of output partitions. You can set this number using spark.sql.shuffle.partitions. However, it is almost impossible to know the best number because it depends on your data size and other factors. We have 2 problems here. If we configure a small number of partitions, then the data size of each partition may be very large. A large shuffle partition may cause 2 types of problems. Your task may need a lot of memory to process the partition, and it might slow down juggling data between memory and disk. In the worst case, you may also see an out-of-memory exception. What if you have too many partitions? The data size of each partition may be very small, and there will be a lot of small network data fetch to read the shuffle blocks. The point is straight. Your query performs slow because of the inefficient network I/O. The large number of partitions will also result in many tasks and put more burden on the Spark task scheduler. Make sense? Great. To solve this problem, we can set a relatively large number of shuffle partitions at the beginning and enable adaptive query execution. The AQE feature of Apache Spark will compute shuffle file statistics at runtime and perform 2 things. Determine the best shuffle partition number for you and set it for the next stage. Combine or coalesce the small partitions into bigger partitions to achieve even data distribution amongst the tasks. Make sense? Great. You can enable AQE using the following configuration. The default value of this configuration is false. You have 4 additional configurations to tune the AQE behavior. The first configuration sets the initial number of shuffle partitions. Dynamically determining the best number and setting that value is applied later. AQE starts with this value. This configuration works as the max number of shuffle partitions. The Spark AQE cannot set a number larger than this. This configuration doesn't have a default value. So if you do not set this configuration, Spark will set it equal to the Spark SQL shuffle partitions. Now let's talk about the second configuration. This configuration defines the minimum number of shuffle partitions after coalescing or combining multiple partitions. We do not have a default value for this configuration also. So if you do not set this configuration, Spark will set it equal to the spark.default.parallelism. Make sense? Great. So we learned about how to control the maximum and minimum shuffle partitions for AQE. Now let's talk about the third configuration. The default value for this configuration is 64 MB and it works as an advisory size of the shuffle partition during adaptive optimization. So this configuration takes effect when Spark coalesces small shuffle partitions or splits skewed shuffle partitions. I'll talk about splitting the skewed partitions in the following video. So for now, you can think of this number as an advisory to AQE. The AQE will use this number for determining the size of the partitions and combine them accordingly. Make sense? Great. The last configuration is simple. The default value for this configuration is true. If you set this value to false, Spark AQE will not combine or coalesce smaller partitions. Make sense? So you have 5 configurations. The first one is a kind of master configuration to enable or disable the AQE feature. If you disable it, the other 4 configurations do not take any effect. But if you enable AQE, you can tune it further using the other 4 configurations. Great. That's all for this video. See you again in the following lecture, and I'll talk about the other 2 AQE features. Keep learning and keep growing.